Good evening. Good evening, students. In last class, we are discussing something related to oxidation number, oxidation state, or as we are planning for today lecture also, we'll do balancing of redox reaction. And apart from balancing of redox reaction, we'll start another concept known as equivalent mass. Till now, in previous lecture, we have calculated the oxidation number of unknown compounds either with the help of algebraic sum or by knowing the structure, molecular structure of the compound. We have seen the definition of reduction, oxidation, reducing agent, and oxidizing agent. In the same continuation, we have just started the balancing of redox reactions. And if you remember the last example of balancing, there may be many balancing can be possible, but typically balanced redox reaction has a unique coefficients. So there are certain steps in which you can balance the reaction. I can take few examples to balance the reaction. We'll consider few steps also. So let's say start balancing, balancing of redox reaction first, and then we'll see concept of equivalent mass also. In balancing of redox reaction, let's say this may be the first example related to balancing. It is, let's say, typically FeSO4. Let's say it is ferrous sulfate. Ferrous sulfate when treated with, KMnO4 potassium permanganate in presence of H2SO4 as a medium. Its product may be, let's say, Fe2SO4 whole thrice. Its product may be MnSO4. Its product may be K2SO4, and its product may be water. So without proper step, it is going to be very difficult to balance this type of redox reaction. So you have to understand there are some specific steps, specific method to balance the redox reaction. So as per step 1 of reaction is, step 1, identify reducing and oxidizing agent. You have to identify which one is reducing agent, which one is oxidizing agent by seeing the change in oxidation number. For example, in the case of ferrous sulfate, iron having +2 oxidation number, as sulfate total charge is found to be -2. In the case of manganese, oxidation number of KMnO4, or in the case of oxidation number of manganese in KMnO4 is concerned, is found to be +7, as potassium oxidation number is +1. In the case of ferric sulfate, iron having oxidation number as +3, and in the case of manganese, its oxidation number is found to be, let's say, +2. So once FeSO4 treated with KMnO4, it will convert into ferric sulfate and, let's say, MnSO4. So first thing is you have to identify reducing and oxidizing agent and convert given reaction into ionic form. Identify reducing and oxidizing agent and convert given reaction into ionic form, which consist all ions, which consist all relevant ions. Which consist all relevant ions and molecule for which there is change in oxidation number. So identify reducing and oxidizing agent and convert given reaction into ionic form. The ionic form reaction should consist all relevant ions and molecule for which there is change in oxidation number. For example, in the case of, let's say, ferrous sulfate, these ions are going to be, ferrous ion and sulfate ion. And in the case of ferric sulfate, these ions is going to be Fe3 plus and sulfate ion. So as there is no change in oxidation number, correspond to sulfate ion, so there is no need to write sulfate ion here. So you have to just write, let's say, Fe2 plus only. Similarly, as per KMnO4 is concerned, KMnO4 can ionize to give, let's say, K plus and permanganate ion. And in the case of MnSO4, it will give Mn2 plus and sulfate ion. So again, there is no change in oxidation number correspond to any atom present in sulfate ion, but we have change in oxidation number for manganese. So it is Fe2 plus when treated with Fe2 plus when treated with, let's say, permanganate ion, it get converted into Fe3 plus, and let's say it get converted into Mn2 plus. So this is the first reaction. Ferrous ion get converted into ferric ion, and permanganate ion can be reduced to, let's say, magnate ion, which is Mn2 plus. In step 2, let's say. In step 2, separate reduction and oxidation half. Separate reduction and oxidation half, and balance their oxidation number. Separate reduction and oxidation half and balance their oxidation number by adding proper number of electron on either side. So you have to separate reduction and oxidation half and balance their oxidation number by adding electron, by adding proper number of electron, you can say, by adding proper number of electron on either side. I hope you have noted down this, step 1 and step 2. For example, step 2 is, in this case, you have to separate, let's say, reduction half and oxidation half. In this case, it is Fe2 plus is converting to, Fe3 plus, and permanganate ion get converted into, it is Mn2 plus. If ferrous ion get converted into ferric ion, it will lose 1 electron, and when permanganate ion will convert into Mn2 plus, it will gain, let's say, 5 electron here. Since if you see oxidation number of manganese is +7, it get reduced to +2 from +7. So this reaction need to be multiplied by 5 such that we have loss of 5 electron and we have gain of 5 electron. So corresponding reaction may be, let's say, 5 Fe2 plus permanganate ion is converting to 5 Fe3 plus, and we have Mn2 plus. So ferrous get converted into ferric ion, and let's say permanganate ion get converting to manganese 2+. Now, if you see step 3, now if you see, let's say step 3, balance. Balance hydrogen and oxygen atom. So balance hydrogen atom by adding H2O and OH minus on opposite side, and to balance oxygen atom H plus and H2O should be added. So balance hydrogen atom by adding H2O and OH minus on opposite side, and to balance oxygen atom H plus and H2O should be added. So if you see in given reaction, 5 Fe2 plus permanganate ion is converting to, let's say, 5 times of Fe3 plus and Mn2 plus. On left hand side we have 4 oxygen atom extra, and on product side there is no oxygen atom. So in balancing of reaction, let's say it is 5 Fe2 plus it is permanganate ion. Once it is converting to 5 Fe3 plus and Mn2 plus, you have to add, let's say, 4 H2O on this side, and you have to add, let's say, 8 H plus on this side, correspond to, let's say, this oxygen atom. We have 4 oxygen atom on both sides. So 5 Fe2 plus permanganate ion is converting to 5 Fe3 plus Mn2 plus. On this side we have 8 H plus, on this side we have 4 H2O. Now as per complete reaction is concerned, it is 5 Fe2 plus it is permanganate ion, and it is 8 H plus is converting to 5 Fe3 plus let's say Mn2 plus, and let's say we have 4 H2O. So now this is the balance reaction, and this balance reaction need to be converted into original form. In original form, Fe2 plus was present in the form of FeSO4. Permanganate ion has to be present in the case of KMnO4. H plus has to be present in the case of H2SO4. So as per step 4 is concerned, let's say convert given balanced redox reaction into original form. Convert given balanced redox reaction into original form by adding suitable number of electron. Convert given balanced redox reaction into original form by adding suitable number of electron or by adding suitable number of ions on both sides. For example, till now the reaction is 5 Fe2 plus. It is permanganate ion. It is 8H plus is converting to 5 Fe3 plus Mn2 plus, and let's say it is 4H2O. So till now we have to balance this reaction up to this much, but you have to convert ferrous ion into ferrous sulfate. So you need to add, let's say, 5 sulfate correspond to, let's say, 5 sulfate ion and equal number of sulfate on opposite sides, such that we do not disturb this already balanced reaction. Now, if you have to write this reaction into original form, these two, 5 ferrous and 5 sulfate, may be written as, let's say, 5 FeSO4. It may be written as, let's say, 5 FeSO4. On the left hand side, we have permanganate ion, and the right hand side, we have, let's say, so permanganate ion has to be written in terms of, potassium permanganate. So you have to add 1K plus on this side and 1K plus on the other side. So again, this much you can write easily in the form of KMnO4. H plus, there's only one source of H plus in original reaction, which is H2SO4. So you need to add 4 sulfate ion here, such that it gets converted into, let's say, 4H2SO4. Overall reaction may be written as, let's say, and then you have to add 4 sulfate ion on the side also. So now the reaction may be written as, let's say, 5/2 Fe2SO4 whole thrice correspond to 5 Fe3 plus. Another coefficient may be, let's say, it may be written as MnSO4 plus, it may be, let's say, half K2SO4, and it may be, let's say, 4H2O in the balance reaction. If you think, let's say, the coefficient of 5/2 and half has to be rationalized, so you can multiply the overall reaction by 2. So the overall reaction may be, let's say, 10 FeSO4 plus, it is 2 KMnO4, 2 KMnO4 plus, it is 8 H2SO4 is converting to 5 Fe2SO4 whole thrice plus, it is 2 MnSO4 plus, it is K2SO4 plus 8H2. So 10 FeSO4 plus 2 KMnO4 plus 8 H2SO4 will give 5 ferric sulfate plus 2 KMnO4, 2 MnSO4 plus K2SO4 plus 8 H2O. So without knowing these proper steps, it is going to be impossible to balance such type of redox reaction. So you have to consider these step 1, 2, 3, and 4 to balance these type of reactions. I will balance one more reaction for you such that you will have better idea for balancing of this type of reactions. I hope you have noted down this reaction 1 for balancing. Another reaction I can balance for you is, let's say, second reaction. I will take some different reaction here. For example, if it is, let's say, I2 in presence of, let's say, dichromate ion in presence of acidic medium, it get converted into, chromium 3 plus, it get converted into IO3 minus, and let's say plus H2O. So if you remember step one for balancing is, you have to identify reducing agent and oxidizing agent, and you have to convert given reaction into ionic form, which should consist all relevant ions and molecule for which there is change in oxidation number. So as per, let's say, reducing and oxidizing agent is concerned, oxidation number of iodine is 0 here, and it is going to be, let's say, +5. Oxidation number of chromium is +6 here, and oxidation number of chromium is +3 here. So as per step 1 is concerned, you can say I2 iodine. I2 can convert into, it is IO3 minus, or overall reaction I2 plus, let's say, Cr2O7 2 minus is converting to chromium 3 plus, and it is IO3 minus. It is going to be the step 1 for the reaction. Similarly, let's say step 2. Step 2 is, you have to separate reduction half and oxidation half. So oxidation half may be, let's say, I2 is converting to, IO3 minus, and it is Cr2O7 2 minus is converting to, let's say, chromium 3 plus. So I'm repeating again, I2 is converting to IO3 minus, and dichromate ion is converting to, let's say, Cr3 plus. If you balance this reaction, it will be twice of chromium 3 plus. In given step, you have to balance their oxidation numbers. As per oxidation number is concerned, it is 0 here, and it is going to be +5. So overall charge of iodine on the left hand side is 0, and on the product side it is +10. So you have to add, let's say, 10 electrons here. Similarly, here chromium oxidation number is found to be +6, and here chromium oxidation number is found to be +3. So left hand side chromium is 12, and product as per chromium is concerned is found to be, let's say, 6. So from +12 it is going to be +6, and you have to add, let's say, 6 electrons here. So I2 is converting to IO3 minus by the loss of 10 electron, and dichromate ion can gain 6 electron. It will convert into 2 chromium 3 plus. Once you add both oxidation and reduction half in step 2, you need to multiply this reaction by 5, and this reaction by 3, such that loss of 30 electron and gain of 30 electron can be balanced out, such that overall reaction should be, let's say, 3I2 plus 5 dichromate ion is converting to, let's say, it is 6 IO3 minus plus 10 chromium 3 plus. It is 10 chromium 3 plus. Then the next step, step 3. You have to balance their oxygen or hydrogen atom. On the reactant side, as per total number of oxygen atom is concerned, it is 35 oxygen atom, and the product side we have 18 oxygen atom. So 35 minus 18, 17 oxygen. 17 oxygen is less on product side, so we have to add 17 H2O. So we have to add 17 H2O and you have to add 34 H plus here. So overall balance reaction should be, let's say 3I2 plus it is 5 dichromate ion plus 34 H plus should convert into, it is 6IO3 minus, it is 10 chromium 3 plus it is 17 H2O. In this case, there is no need for step 4, as already reaction is given in ionic form. So with the help of few steps, around 3 to 4 steps, you can balance any of the complex redox reaction. I hope it is clear to you. I hope you have noted down this now. I can take one more example for you to balance the reaction. Let's say third reaction to balance is, it is zinc when treated with HNO3. It will be zinc nitrate plus N2O and plus H2O. So it is zinc plus HNO3 will convert into zinc nitrate plus N2O plus H2O. So as per oxidation number of zinc is concerned, it is zinc having 0 oxidation number and it is plus 2 oxidation number. In the case of nitrogen, it is plus 5 oxidation number, it is plus 1 here. So zinc is converting to zinc nitrate and HNO3 get converted into N2O. So again, as per step 1 is concerned, you have to convert given reaction into ionic form. It should consist all the ions and molecule which have change in oxidation number. So this reaction is going to be zinc plus HNO3 can ionize to give H plus and nitrate ion. There is no need to write H plus here, as no change in oxidation number correspond to hydrogen. So it is zinc plus nitrate ion is converting to zinc 2 plus and it is converting to N2O. We have change in oxidation number correspond to zinc atom, nitrate ion, zinc 2 plus and N2O. Step 2. You have to separate reduction and oxidation half. So if it is zinc converting to zinc 2 plus and it is nitrate ion converting to, let's say, N2O. So if zinc converting to zinc 2 plus, it will lose, let's say, 2 electron here. And similarly, if nitrogen from oxidation number of +5, it decreases to oxidation number of +1. So overall, from +10 charge on the reactant side on nitrogen and +2 charge on the product, it has to be, let's say, overall, 8 electrons can be added here. So from +10 oxidation number, it is going to be +2 oxidation number. In this case, let's say this need to be multiplied by 4. And overall reaction should be, let's say it is 4 zinc plus, let's say, 2 nitrate ion is converting to 4 zinc 2 plus and N2O. In step 3, you have to balance oxygen atom. On the reactant side, already we have 6 oxygen atom, and on the product side we have just 1. So we have to add 5 H2O on this side. So 5 H2O, and we have to add 10 H plus on this side. So it is already balanced reaction, but it's the balancing in ionic form. As per step 4 is concerned, you have to convert given reaction back into original form. For example, a zinc, 4 zinc is already in the form of 4 zinc, but H plus comes from HNO3. So you need to add additionally, 8 nitrate ion on this side and 8 nitrate ion on this side, such that we have 8 HNO3. Overall balance reaction, should be, in overall balancing, it is 4 zinc plus it is, let's say, 10 HNO3 is converting to, let's say, 4 zinc nitrate plus N2O plus 5 H2O. So this is eventually balanced redox reaction here. So 4 zinc plus 10 HNO3 is converting to, let's say, 4 zinc nitrate plus N2O plus 5 H2O. So if you see overall balance reaction, it is 4 zinc plus 10 HNO3 is converting to 4 zinc nitrate plus N2O plus 5 H2O. So till now we have just seen balancing, balancing of redox reaction. So apart from balancing of redox reaction, the next topic is going to be, equivalent mass. Equivalent mass. So equivalent mass is amount of any substance. Amount of any substance which can react or displace directly or indirectly, amount of any substance which can react or displace directly or indirectly, 1 gram of hydrogen, 8 gram of oxygen, or 35.5 gram of chlorine, let's say Cl2. So amount of any substance which can react or displace directly or indirectly, 1 gram of hydrogen, 8 gram of oxygen, or 35.5 gram of chlorine, etc. We'll see the meaning of etc. and we'll see the meaning of directly, indirectly. For example, magnesium when react with 2HCl, it will convert into magnesium chloride and hydrogen gas in displacement reaction. If you see in given balance reaction, 24 gram of magnesium can displace 2 gram of hydrogen. And if you see in the case of, let's say, 2HCl, out of this 2HCl, it is nothing but 2 gram and it is nothing but 71 gram. So 24 gram of magnesium can combine with 2 gram of hydrogen, can combine with 71 gram of chlorine, can displace 2 gram of hydrogen here as per balance reaction is concerned. So you can say to displace 1 gram of hydrogen, or to react with 1 gram of hydrogen, mass of magnesium required should be equal to 24 divided by 2, and it comes out to be 12 gram. So to displace 1 gram of H2 or to react with 1 gram of hydrogen, mass of magnesium required should be equal to 24 by 2 gram, which comes out to be, let's say, 12 gram. So the meaning of equivalent mass, amount of any substance which can react or displace directly or indirectly 1 gram of hydrogen, 8 gram of oxygen, or 35.5 gram of chlorine. For example, magnesium when react with, let's say, HCl, it produces MgCl2 and hydrogen gas. To displace 1 gram of H2 or to react with 1 gram of hydrogen, mass of magnesium required should be nothing but 24 by 2 gram, comes out to be 12 gram. So as per definition of equivalent mass is concerned, can we say equivalent mass of magnesium is the mass which can displace 1 gram of hydrogen or which can react with 1 gram of hydrogen? It means this is same as equivalent mass of magnesium. So it is same as equivalent mass of magnesium comes out to be 12 gram. I hope now it is clear the definition of equivalent mass. 12 gram of magnesium can displace 1 gram of hydrogen, as 24 gram of magnesium can displace 2 gram of hydrogen. So it is the mass which can react or displace 1 gram of hydrogen, 8 gram of oxygen, or 35.5 gram of chlorine. Further, we'll do two simple questions based on this. Let's say question number 1 is, if are given if a given metal hydride consists of 5% hydrogen. If a given metal hydride consists 5% hydrogen, then find out, equivalent mass of metal. If given metal hydride consists 5% hydrogen, you have to find out equivalent mass of metal. So as far as metal hydride is concerned, out of metal hydride, let's say out of 100 gram, out of 100 gram of metal hydride, as it consists 5% hydrogen, so I can simply say it consists 5 gram of hydrogen, and obviously it consists 95 gram of metal. So out of 100 gram of metal hydride, it consists 95 gram of metal and 5 gram of hydrogen. As per its definition is concerned, let's say out of 100 gram, it consists 5% hydrogen. So as per equivalent mass is concerned, to combine with let's say 1 gram, to combine with 1 gram of hydrogen as per definition of equivalent mass is concerned. So 5 gram of hydrogen can combine with 95 gram of metal. So to combine with 1 gram of hydrogen, equivalent mass of metal is 95 divided by 5 comes out to be 19 grams. If a given metal hydride consists 5% hydrogen, find out equivalent mass of metal. In any metal hydride, which is let's say 100 gram, 95 gram of metal, and we have 5 gram of hydrogen. To combine with 1 gram of hydrogen, equivalent mass of metal, 5 gram can combine with 95 gram of metal. So 1 gram can combine with 19 gram of metal, which has to be by definition equivalent mass of metal. Next question. On burning of metal, if its mass is increased, on burning of metal, if its mass is increased by 24%. On burning of metal, if its mass is increased by 24%, then find out equivalent mass of metal. On burning of metal, if its mass increased by 24%, then find out equivalent mass of metal. So as per its equivalent mass is concerned, once we see metal, the burning means obviously its reaction with oxygen gas such that it get converted into, metal oxide solid. In the case of metal, suppose it is 100 gram of metal, and if it gave 124 gram of metal oxide, it means 24 gram of oxygen has to be combined with 100 gram of metal to get total mass of metal oxide as 124 gram. So I'm repeating again, metal when combined with oxygen, it can give metal oxide. 100 gram of metal can combine with 24 gram of oxygen and it give 124 gram of metal oxide. Further, as per definition of equivalent mass is concerned, which can combine with 8 gram of oxygen. So, with 8 gram of oxygen, mass of metal combined should be equal to, it is, for 100 gram of metal, oxygen combined is nothing but 24 gram. So it is, divided by 24 and need to be multiplied by 8 and comes out to be 33.3 gram. So I'm repeating again, 24 gram of oxygen can combine with 100 gram of metal. So 8 gram of oxygen can combine with 8 gram of oxygen can combine with 33.33 gram of metal. This is the same as by definition equivalent mass. So, equivalent mass of metal should be nothing but, let's say, 33.33 gram. So I'm repeating again, the basic definition of equivalent mass. It is the mass which can combine with, 1 gram of hydrogen. It is the mass which can combine with 8 gram of oxygen, or it is the mass which can combine with 35.5 gram of chlorine. Next is, let's say, you can see in general formulae for equivalent mass. Formulae for, equivalent mass. So, in general, equivalent mass equal to, molecular mass or molar mass divided by, it is n factor. In general, equivalent mass should be equal to molecular mass divided by n factor, where n should be equal to, valency for element. It is equal to basicity for acid it is equal to acidity for base. So where N, let's say equal to valency for element, equal to basicity for acid, it is equal to acidity for base. Same as per N is concerned, it is, total positive or negative charge on its ions per molecule. So N is valency for element, basicity for acid, acidity for base. It is total positive or negative charge on its ions per molecule for salt, let's say. We'll see the meaning of basicity of acid is the number of replaceable H plus ion. Acidity is number of OH minus ion which are replaceable from base. And it is total positive or negative charge on its ion per molecule for salt. It is equal to, total number of electron transfer in, balance redox reaction per atom or, per molecule. Where N is valency for element equal to basicity for acid. It is acidity for base. It is total positive or negative charge on its ion per molecule for salt. It is total number of electron transfer in balance redox reaction per atom or per molecule. One by one, I can see few examples related to equivalent mass. But as per the denominator factor, N factor is concerned, this N factor is valency for element, it is basicity for acid, it is acidity for base, it is total positive or negative charge on its ions per molecule for salt, and it is total number of electron transfer in balance redox reaction per atom or per molecule. For example, let's say one by one, you can see 4 elements as per equivalent mass of sodium is concerned, it is 23 divided by 1. As per magnesium is concerned, it is 24 divided by 2. As per aluminum is concerned, it is 27 divided by 3. So 27 atomic mass divided by aluminum का valency is 3. Magnesium के लिए it is 24 divided by 2. 24 is the atomic mass divided by 2. Sodium, it is atomic mass 23 and then divided by 1. Similarly, for acids, equivalent mass of HCl should be its molecular mass divided by 1. As per molecule, only one H plus is replaceable, and as per HCl is concerned, it is mono basic acid. Similarly, if it is H2SO4, it is M by 2. In the case, let's say M dash, you can say. In the case of H3PO4, it can be M double dash divided by. So one acid is monobasic, another is, it is dibasic, and another you can say it is tribasic acid. So monobasic acid, dibasic acid, and let's say tribasic acid. Similarly, for base, for any base equivalent mass, for example, equivalent mass of NaOH is molecular mass divided by 1. In the case of, let's say, calcium hydroxide, it is M divided by 2, as NaOH is monoacidic base. Calcium hydroxide is, diacidic base. So for base, NaOH is monoacidic base. For calcium hydroxide, it is, diacidic base. So it is M divided by 1. You can say it is M dash divided by 2 in the case of base. So for any element equivalent mass, for example, for sodium, it is 23 by 1, magnesium, it is 24 by 2, aluminum, it is 27 by 3. Same in the case of different acids and base. For HCl, it is M by 1, H2SO4, it is M dash by 2. In the case of S3PO4, it is M double dash divided by 3. And similarly, in the case of bases, NaOH or calcium hydroxide, in general, for any salt, let's say, for salt, equivalent mass should be equal to, equivalent mass of, suppose NaCl should be its molecular mass divided by 1. Obviously, total positive charge on its ion. Either you can say it is +1 or you can say it is -1. Same, let's say equivalent mass of magnesium chloride. Total charge on magnesium is +2, and for 2 chloride ion, it is same as -2. So it is going to be, let's say, M divided by 2. Same in the case of equivalent mass of, calcium phosphate. Equivalent mass of calcium phosphate may be, let's say, M divided by 6 as total. As total, in the case of calcium, it consists +2 charge. So overall calcium charge is found to be +6. And in the case of phosphate ion, total negative charge on the phosphate ion is also, let's say, -6. Similarly, for redox reaction, in general, for any redox reaction, for example, the redox reaction may be, let's say it is zinc when treated with V2O5 is converting to zinc oxide and vanadium. This is nothing but, its balance reaction may be, it is 5, and it is 2 here. Now, as far as zinc is concerned, zinc is reducing agent here, and V2O5 is oxidizing agent. Now, as per reducing agent zinc is concerned, in this case, zinc having 0 oxidation number and it is +2 oxidation number. Vanadium is found to be +5 and 0 oxidation number here. So as per reducing agent is concerned, its equivalent mass should be, its equivalent mass should be, let's say its atomic mass divided by, it is number of electron transfer. So as per zinc is concerned, its atomic mass is 65 divided by number of electron get transferred per atom. So zinc having 0 oxidation number, and in the case of zinc oxide is found to be +2. So it is 65 divided by 2. Same in the case of oxidizing agent, equivalent mass. In the case of oxidizing agent, equivalent mass should be equal to, their molecular mass divided by 10. Their molecular mass divided by 10. As per V2O5 is concerned, overall vanadium atom is found to be 10 here, 5 into 2, and then this M dash divided by 10. Overall, as per oxidizing agent is concerned, equivalent mass of oxidizing agent and similarly equivalent mass of reducing agent. So in general, it is equivalent mass is, molecular mass divided by n factor. N factor can be valency for element, it is basicity for acid, it is going to be acidity for base, it is going to be total positive charge or negative charge on its ions per molecule for salt. It is number of electron get transferred. Is a number of electron get transferred per molecule or per atom in the case of redox reaction. In the case of reducing or oxidizing agent, so overall, in a given amount, let's say this amount is given in the mass of, let's say, grams, let's say, in the amount. So in a given amount, which is given in grams, here you can say number of moles. Number of moles is, let's say, amount given divided by, it is molar mass. Number of moles is amount given divided by molar mass. And similarly, it is nothing but number of equivalents should be equal to amount given divided by. Instead of molar mass, here you can say, let's say it is equivalent mass. So number of moles is nothing but amount given divided by molar mass, and number of equivalents is nothing but amount given divided by equivalent mass. Should be equal to amount given divided by, instead of equivalent mass, it should be molar mass divided by n factor. Amount given, instead of equivalent mass, it is molar mass divided by, n factor. We have just seen this. From here, you can say it is n factor and amount given divided by molar mass. Amount given divided by molar mass is number of moles, and from here, number of equivalents should be equal to n factor multiplied by number of moles. Now, number of equivalents is n factor multiplied by number of moles. So you have to remember this expression as number of equivalents is n factor multiplied by number of moles. Is the n factor is the same, it is valency for element, it is basicity for acid, it is going to be acidity for base. I hope you have noted down this. Number of equivalents is n factor times of number of moles. Okay, let's move further. So the next thing is, law of equivalence. It is law of equivalence in any chemical reaction. In any chemical reaction, same number of equivalents of different reactants. In any chemical reaction, same number of equivalents of different reactants get consumed and they produce exactly same number of equivalents of any of the product. So in any chemical reaction, same number of equivalents of different reactants get consumed and they produce exactly same number of equivalents of any of the product. for example, during given double displacement reaction. During given, double displacement reaction. So this reaction is going to be, let's say, Na3PO4 plus CaCl2 is Ca3PO4 whole twice, and let's say it is NaCl in balance reaction. So if you balance this reaction, normally it is 3 calcium, it is 2 here, and it is 6 NaCl. As per balance reaction is concerned, you can say it's 2 moles can react with iska 3 moles, can produce 1 mole and 6 moles. So 2 moles of Na3PO4 can combine with 3 moles of CaCl2, can produce 1 mole of calcium phosphate and produce 6 mole of NaCl. Now, as per number of equivalence is concerned, or first you can say as per their n factor as a salt is concerned. Do you think its n factor is going to be 3, as total positive charge on its cation is going to be 3 plus, and total negative charge on this iron phosphate is going to be minus 3. So total, let's say, n factor is going to be 3 here. In this case, its n factor is 2. In this case, its n factor is 6, and its n factor is found to be 1. So as per number of equivalence is concerned, number of equivalence, it is 2 moles multiplied by n factor. So it is 6 equivalence. It is going to be 6 equivalence, 6, and going to be 6 equivalence. So as per number of equivalence is concerned, it is n factor multiplied by number of moles. So as per Na3PO4 is concerned, or CaCl2 is concerned, calcium phosphate or NaCl is concerned, all they consist same number of equivalence as 6 equivalence each. So they can have different number of moles, but they always consist same number of equivalence. So in any chemical reaction, total equivalence of one of the reactant get consumed will be same as number of equivalence of another reactant get consumed. So further you can say in any redox reaction, in any, suppose, neutralization reaction, in any neutralization reaction, total equivalence of acid should be equal to total equivalence of base. In any neutralization reaction, total equivalence of acid should be equal to total equivalence of base consumed. And similarly, if you see in any redox reaction, it is total equivalence of reducing agent should be equal to total equivalence of oxidizing agent. So in any redox reaction, total equivalence of reducing agent should be equal to total equivalence of oxidizing agent. I hope it is going to be clear. Are you able to understand the law of equivalence? Yes, so have you noted down this? So total till now, at least we have revised the concept of mole and stoichiometry. In the next lecture of mole and stoichiometry, we can do just few questions based on this. So it is going to be your assessment related to moles and stoichiometry, which is going to be tomorrow only. So just revise your class notes from, let's say, lecture 1 related to mole and stoichiometry. So till now we have seen definition of moles and its application. Then we know basic moles calculation and stoichiometry. Then we have done concentration terms, including molality, percentage by weight. Then we've seen definition of oxidation number, oxidation state, balancing of redox reaction, and the concept of equivalent mass. So as per today's lecture is concerned, I will do this much only. Huh? Okay. So anyway, I'm going to finish my lecture now.